Hello students, this is the last part of chapter 6 and we're going to be discussing equilibria as well as energy diagrams to help us understand why reactions occur and the product distributions associated with them. So just to refresh everyone's memory, reactions are reversible and at equilibrium they may vary in the concentrations of reactants and products depending on what you start with, but what's not varied is the equilibrium constant K at a given temperature and pressure. So just remember, based on this general reversible reaction, you have products in the numerator, reactants in the denominator. When products are dominant, meaning the reaction lies more to the right, K will be very large. So we're going to look at that. You can predict the amounts of reactants and products knowing Kc. If Kc is really small, you mainly have reactants. Somewhere in between, you have both present. So we already looked at adding HBr to an alkene. If I just put any mixture of any of these products and reactants together, these can go in between and an equilibrium is established. Knowing the KEQ of this, products over reactants, is 7.5 times 10 to the 7, that huge number tells me, because the product is in the numerator, that this mainly lies to the right. So if I add in a bunch of reactants at equilibrium, it'll eventually funnel over to give me the product, the bromoalkane. So hopefully you can see how powerful that is. You can use that to your advantage to synthesize certain substances. Also, I want to remind you of the relationship between delta G and KEQ. The reason is a lot of times we're going to be looking at delta G for either reactions or energy differences between different conformers. So delta G, Gibbs free energy, is minus RT natural log of KEQ. So just looking at this, if K is large, delta G is negative. So hopefully you remember this from a previous chemistry course. Energy is released, delta G is negative, into the surroundings. So that's a favorable process. We called this exergonic. If K is very small, less than 1, delta G is positive. And in that case, then the energy is absorbed from the surroundings, and we call this endergonic. The reaction is unfavorable. So why is a negative delta G favorable? Have you ever thought about that? In short, it's because the universe tends towards disorder and tends towards the release of energy. So recall also that delta G equals delta H minus T delta S. Delta H is enthalpy. This is related to energy of bonds breaking, bonds forming. And delta S is disorder. So if there's more disorder in the universe, this becomes more negative. If heat is released and enthalpy is negative, this becomes negative. So both of those are favorable towards a reaction occurring, making delta G negative. At the core, a reaction does involve bond breaking and bond forming. So here's an example. We've seen the homolytic cleavage of chlorine to give its 2 radicals. That costs you energy. And the reason why it's important to look at these sort of energies is because when you sum them up, the products minus the reactants, those that are forming versus those that are being broken, in the end, that'll give you an indication of whether the whole reaction is exothermic or endothermic, meaning delta H is negative or positive. So the one thing I want to point out to you is that delta G is based on delta H and delta S, but I'm going to tell you that delta H is the dominant factor. It plays a bigger role in whether or not delta G is negative or positive. So we need to be able to translate this to energy diagrams. And the reason is that this is our way to have a picture of competing reactions, the influence of different intermediates. So let's just get situated in looking at this energy diagram. On the y-axis, there's potential energy. So the higher you're up here, the higher the energy, and the x-axis is a reaction coordinate. So it's a progress of the reaction. Potential energy, we can either, depends on what you're looking at. Maybe you are looking at delta H, it could be delta H. Maybe you've got information on delta G, it could be delta G, either. You always start with reactants or products. Reactants at some energy level. The products may be below, lower in energy, meaning the products are more stable. The lower in energy, the more stable. So going from reactants to products, overall I release energy. That's based on bonds broken, bonds formed. The products are higher in energy than the reactants. So the other feature here is there's always some hill to climb. We call that activation energy or delta G double dagger. Double dagger because the top of the hill is called the transition state with a double dagger. So the activation energy is a hill to climb to get the reaction kick-started. There's a reason why that reactions don't just spontaneously go all the time. It's because you need a certain energy to put into it to get it started. So the reactants are just sitting around. But if I give it enough energy, heat it up, then it can reach this hill, get involved in a transition state, which means the atoms rearrange, bonds break, bonds form, and then it can, in this case, release energy overall to form the products. The net difference between reactants and products will be your delta H or delta G. So overall, reactants go through a transition state, kind of the in-between of bonds breaking, bonds forming, and then form a product. So is this endergonic or exergonic? Before we get to that, let me ask you, or let me tell you this, transition states, I mentioned it's this between bonds breaking and forming. So they're very unstable. They can't be isolated. They have a finite lifetime. This is not something you can like collect in a funnel in the lab. So here's our endergonic and exergonic discussion. The energy diagram I showed on the previous slide looks like the one on the right. That's exergonic, overall releasing energy. Endergonic is overall absorbing energy. You start out with the reactants at a lower energy, and then you increase the energy, climb this hill, but you never really release fully down. You just release a little bit. So your products are higher in energy. There is a situation where you do have intermediates. We've already seen this. We've seen this in the reaction of the alkene adding HBr. What's the intermediate you form? You form a carbocation. These are very, very reactive, short-lived species, but they have been isolated in certain situations. So these are a stop on the energy diagram. So instead of one hump, reactant, transition state, and product, you go reactant, transition state, and it's your first transition state, and then the intermediate. For that last example, it'd be the carbocation, and then the carbocation will undergo a transition state where for example, Br bond to carbon is starting to form, and then eventually you will form your product and release energy. And again, this is an example of exergonic. So just take a step back. If you have one intermediate, you have two hills. If you have two intermediates, you'd have a third hill. The other thing is reactants and products. Sometimes products can be higher in energy. The maxima, the tops of the hills, are the transition states. The minima are intermediates. Okay, the last thing I want to talk about are catalysts, because this is important because in our bodies or sometimes in the lab, we cannot achieve some super high energy cost to climb the hill. So catalysts are used to lower the activation energy. So without a catalyst, you're up here. You need to climb this giant mountain. But with a catalyst, you're here. So you can climb just a little bit different. And sometimes you'll see this just as a single hill. That doesn't matter. But catalysts are a little more complicated. So effectively, it lowers the activation energy. And this occurs a lot in biological systems where moderate temperatures are required to avoid overheating an organism. In the lab, I want to show you one example. You can add HH across alkene bond here, the double bond. But that is hard to do sometimes. So a catalyst that helps are certain metals like platinum or palladium. And what you can do is take the metal surface, the catalyst surface, so this is a metal, just think of like metal atoms, and you can add hydrogen gas to it to attach H's. And then when you introduce the alkene pi bond coordinates to the metal, and then now it's set up for the metal surface to more easily transfer the H's to give you the desired alkane product. Okay, that concludes chapter 6. You guys are all primed and ready to begin chapter 7, which starts talking more about alkene reactions.